Good afternoon, once again. Welcome to my YouTube channel, Pearson and Excel International Maths. And today I want us to discuss about fixed point iteration. You have not had iteration before. We are still in numerical methods on page 163. We have learned that numerical methods, we have been trying to acquire the root of a function in terms of x when fx is equals to 0. We were trying to get x when fx is equals to 0, and that is the root of a particular function. Now, in iteration, we are told that an iterative method can be used to find a value of x for which fx is equals to 0. And to perform an iterative procedure, it is usually necessary to manipulate the algebraic function first. And what are we saying? To solve an equation of the form fx is equals to 0 by an iterative method, it is important to rearrange fx is equals to 0 into the form x is equals to gx. Yani, in other words, you make one of the x's in the original function the subject of the formula. Of course, that demands that you have a different function altogether, and use the iterative formula xn plus 1 is equals to gxn. Of course, for you to get the next root, you have to operate the previous value of x under g. Some iterations will converge to a root, and this happens, of course. Okay, let me just go direct to explaining what we mean by converging iterations. And sometimes you may have two functions. For example, we may have a function that is x squared, or rather x squared, or rather let's talk about f of x is equals to x squared minus x minus 1. And you may want to just make probably one of these x's here the subject of the formula. And by this, you'll be saying when fx is equals to 0, then x squared minus x minus 1 is equals to 0. And you may want to make x squared the subject. You may have x squared is equals to x plus 1. But we need x, we don't need x squared. And this follows that x is equals to the root of x plus 1. This is just an example of that iteration formula for this particular function. At some point, you may also make this x the subject of the formula, either way, so long as it helps you to work out the question. You may have another equation which is fx is equals to x, and I mean this is just the equation y is equals to x. So the moment you combine the two in this kind of a diagram, this is what we call staircase diagram. A staircase diagram. Let me just display it there. Okay, we have this graph of y is equals to x in the same graph. Let's have it here. Y is equals to x. This is just y is equals to x. And we have this other graph that talks of we can talk about y is equals to the root of x plus 1. Those could be the graph that you are dealing with. There is y there, and there is x there. There is 0 there. Sometimes we may have a value of x in both of the graphs, and we may call it x naught. It will give you this value of y for one function and this value of y for the other function. And you realize that the two values of y's are very far from each other. So what you need to do is use that value of x, use that value of x, that value of x to draw a straight line which is very horizontal, and at that point we get another value of x1. Now when you substitute x1, you can see the value of y are now closer when you're using x1, but because they are not as close, we may talk of another horizontal movement so that we can land on x3, and the moment we have x3, you can already see that the values of y's are close each other. So if we tend now to get horizontal here and then draw another point x4, so we may realize that this is not x3 but x2. There is x3 there. You may realize that as we move further along the x-axis, we are converging to a point. We are converging to that point, and that is just true. So this is simply called the staircase diagram. This is the staircase diagram. The other method is the method of the cobweb diagram. The other way that an iteration converges is that successive iterations alternate being below the root and above the root. Below the root and above the root. They keep alternating below the root and above the root. These iterations can still converge to the root, and the resulting graph is sometimes called a cobweb diagram. For example, if we have fx equals to the same equation, x squared minus x minus 1, we may want to make probably this x the subject of the formula or anything else, but let us see. We are told that this one can give a formula of, can produce an iterative formula of xn plus 1 is equals to 1 over xn minus 1. How is this possible? Of course, when this is true, x squared minus x minus 1 is equals to 0. And we can easily say that 1 is equals to x squared minus x. And if we take x common there, x minus 1, 1 is equals to 1. And of course, if you divide both sides by x minus 1, you find that this x is going to be, you find that if you talk about x squared minus x minus 1 and take 1 across, 1 is equals to x squared minus 1, and you divide both sides by x minus 1, you'll find that this x is going to be 1 over x minus 1. Now, the next x is now what we're calling xn plus 1. And the previous x is what we're calling xn. So we just talk about xn plus 1, and that is x. So that is very critical. Sometimes you may have something, you may start somewhere. Successive iterations produce the cobweb diagram shown on the right. Of course, if you happen to have such kind of a relationship, this diagram will come up. This diagram will come up. This kind of a diagram is going to come up. And you are going to have y is equals to x because that is true. And you're going to have this equation that looks like This is y is equals to x, and this is the equation y is equals to 1 over x minus 1. If you happen now to get if you happen to identify x naught, you will hit that particular point and walk horizontally. You will hit that particular point and walk horizontally, hit there, and then go down to the graph, hit there, and then go down again to the straight line, to the line y is equals to x, hit there, and then go up to hit the graph, the other graph, you hit there, and then again you go to the straight line, hit there, go down, hit there, go to the straight line, hit there, hit there, hit there, hit there, hit there, and finally it will converge to this particular point. This is now what you call the cobweb This is now what you're calling the cobweb diagram. The cobweb diagram. Now, not all iterations or starting values converge to a root. When an iteration moves away from a root, often increasingly quickly, you say it is diverging or it diverges. Of course, successive iterations diverge from the root, and of course, it can diverge when you have probably that root. When you have this kind of a root, you can have that kind of a graph, and this other one. When you start far away from, the root, you continue to diverge. You continue to diverge. This is going this way, and this is going this way. This is now what we're calling diverging roots, and this one will not give you any root. In fact, we are not even supposed to call them diverging root. It's called diverging diagram, which does not give you any root. Anyway, we are going to use this knowledge. Don't worry whether you understood or not, but for now, this one will be done practically in example 4 and example 5. That is coming handy in the next video. For now, just get that. This is just preliminary. I know it's sinking sooner or later. All right.